For as long as humanity has gazed upon the stars, we've conceived of existence as one singular, immense canvas. Our universe, a boundless expanse of galaxies, stars, and planets. All born from a single cosmic genesis, the Big Bang. We've mapped its edges, deciphered its ancient light, and begun to understand the intricate laws that govern its every particle. But what if this grand narrative, this solitary cosmic epic, is merely a prologue? What if the universe we inhabit, the very fabric of our reality, is not unique? What if it is but a single, shimmering thread in an infinitely larger, impossibly complex tapestry? This isn't the realm of mere fantasy or philosophical musing, though it certainly sparks the imagination. This is the multiverse. A profound, startling, and increasingly compelling concept at the very frontier of modern physics and cosmology. It's an idea that challenges the deepest-seated assumptions about our place in existence, hinting that beyond the visible horizon of our cosmic home, countless other universes might lie, each potentially a distinct reality, with its own unique history, its own set of fundamental laws, and perhaps even its own versions of us. The very notion can feel overwhelming, even unsettling. If there are other universes, how are they formed? What are they like? And perhaps most importantly, why would such an extraordinary idea be taken seriously by the most rigorous scientific minds of our time? The answers, as we shall see, emerge from some of the most stubborn mysteries our universe presents, paradoxes and cosmic coincidences that defy simple explanation. Prepare to embark on a journey that will stretch the limits of your imagination and redefine your understanding of everything. We will explore the leading scientific theories that give rise to the multiverse concept, from the relentless expansion of space-time to the baffling whims of quantum reality. This isn't just about other worlds. It's about re-evaluating the very nature of reality itself. Are you ready to question whether our universe is truly unique, or merely one among an infinite ensemble? To truly begin our deep dive into the multiverse, we must first rewind to the very inception of our own universe, to an era so incredibly brief, yet so profoundly impactful, that it shaped everything we now perceive. Cosmic inflation. It's a concept that might initially seem counterintuitive, an acceleration of space itself, far beyond the speed of light. But it serves as the foundational bedrock for the most widely accepted multiverse model, the Quilted multiverse. Often visualized as a vast cosmic foam, or an endless collection of bubble universes. Understanding cosmic inflation, the Big Bang's missing piece. For decades after Edwin Hubble observed the expansion of the universe, the standard Big Bang model faced some stubborn puzzles. These weren't minor inconsistencies. They were fundamental questions that threatened to unravel the entire theory. The horizon problem. Why is the cosmic microwave background (CMB) radiation, the afterglow of the Big Bang, so remarkably uniform in temperature across the entire sky, even in regions that were causally disconnected and could never have exchanged heat? It's like finding two opposite ends of a vast desert at exactly the same temperature, implying they must have once been in close contact. The flatness problem. Why is the geometry of our universe so incredibly flat? Not curved like a sphere or a saddle, but perfectly flat, implying its total energy density is almost precisely balanced. Any slight deviation in the early universe, and it would have either collapsed back on itself immediately or expanded too quickly to form anything. It's like balancing a pencil on its tip for billions of years. The monopole problem. The Big Bang predicted the existence of exotic, heavy magnetic monopoles, isolated north or south poles. Yet despite extensive searches, none have ever been found. Where did they go? In the early 1980s, physicist Alan Guth proposed cosmic inflation as a brilliant solution to these conundrums. He theorized that in the first incredibly tiny fraction of a second, from about 1036 to 1032 seconds after the Big Bang, the universe underwent a period of exponential expansion, growing by a factor of at least 1026. That's a 1 followed by 26 zeros. Or the size of a proton expanding to a grapefruit in an instant. This wasn't the expansion of matter into pre-existing space. It was the ferocious, superluminal stretching of space itself, driven by a hypothetical energy field dubbed the inflaton field, visualizing inflation's effects, solving the horizon problem before inflation. The entire observable universe was infinitesimally small. A tiny region where all parts were in causal contact and could equalize their temperature. Inflation then blew this uniformly heated region to an immense size, far beyond our current cosmic horizon, explaining the CMB's uniformity. Solving the flatness problem. Imagine crumpling a piece of paper. If you inflate it to an enormous size, any wrinkles or curves become imperceptible, making the surface appear flat. Similarly, inflation flattened the universe, pushing its geometry towards the critical density required for flatness. Solving the monopole problem, inflation diluted the density of any hypothetical magnetic monopoles to an undetectable level, scattering them so widely across the vast inflated cosmos that we're unlikely to ever find one. From inflation to eternal inflation, the multiverse's engine. Cosmic inflation, while incredibly successful at solving these problems, introduced a new, fascinating possibility. What if this rapid expansion, this inflating of space, didn't stop everywhere at once? What if, in certain regions, the inflattened field never truly settled down, causing inflation to continue indefinitely? This is the core concept of eternal inflation. Think of eternal inflation not as a single balloon inflating, but as a vast, ever-expanding metaspace, where new bubbles are constantly nucleating and detaching. Imagine a boiling pot of water. Bubbles of steam are perpetually forming and rising from the surface. In this cosmic analogy, the continuously inflating space is the boiling water and the regions where inflation locally ends, where the inflattened field decays and releases its energy, giving rise to matter and radiation. Become the bubble universes. Our own observable universe, the cosmos we inhabit, would then be just one such bubble. It's a region where inflation stopped, allowing the universe to thermalize, cool, and begin forming the structures we see today. Galaxies, stars, planets, and eventually, us. But in the surrounding larger metaspace, inflation continues relentlessly, perpetually generating new bubbles. The nature of bubble universes. Cosmic islands of infinite variety. The implications of eternal inflation are staggering. If inflation never truly stops globally, then the number of these bubble universes becomes infinite. Each bubble, once formed, expands independently, becoming its own self-contained cosmos. And because the quantum fluctuations that give rise to the end of inflation can vary, the conditions within each bubble can be wildly different. Consider the astonishing diversity implied. Varying physical constants, perhaps. The most profound consequence is that the fundamental constants of physics, those numerical values that define gravity, electromagnetism, and the nuclear forces, could be different in each bubble universe. One universe might have stronger gravity, another, a weaker electromagnetic force. This diversity directly addresses the fine-tuning problem we discussed earlier. If there are infinite universes, with random variations in constants, then it's no longer a miracle that our universe happens to have the precise values conducive to life. It's a statistical inevitability that at least one such universe would exist. We simply find ourselves in one of the habitable ones. Different dimensions. Our universe appears to have 3 spatial dimensions and 1 time dimension, but in other bubble universes, the process of compactification, where extra dimensions curl up to microscopic sizes, might have occurred differently, leading to universes with 5, 7, or even more spatial dimensions, or perhaps fewer. How would life evolve in a 2D or 5D universe? It's almost impossible to conceive. Varying particle content and forces. The specific types of fundamental particles, quarks, leptons, and the interactions between them might also differ. Some universes might lack stable protons, others might have entirely different elementary particles. The vastness of the quilted multiverse means these bubble universes are incredibly distant from each other. The space between them continues to inflate at an exponential rate, pushing them apart faster than the speed of light. This means they are causally disconnected. No light, no information, no force from one bubble could ever reach another. They are, effectively, isolated cosmic islands, each a complete, self-contained reality, forever beyond our direct interaction or observation. This model fundamentally redefines our cosmic address. We are not in the universe. We are in a universe, one bubble among an infinite cosmic foam. a unique patch in an endlessly varied and ever-growing quilt of existence. It transforms our understanding of rarity, suggesting that anything that can happen, eventually will happen, somewhere, in some bubble. As we venture beyond the infinitely bubbling foam of the quilted multiverse, we encounter an even more esoteric, yet equally captivating, vision of reality born from the most ambitious theories in modern physics: the Brane multiverse. This model emerges primarily from the intricate mathematics of string theory and its more encompassing successor, M-theory, which propose a universe far stranger than our everyday experience suggests. The quest for a theory of everything. String theory's promise. For decades, physicists have grappled with a fundamental incompatibility: the stark contrast between Albert Einstein's general relativity, which brilliantly describes gravity, and the large-scale structure of the cosmos, and quantum mechanics, which perfectly governs the bizarre world of particles at the subatomic level. These two pillars of modern physics, while individually incredibly successful, simply do not play well together when applied to extreme conditions, such as inside a black hole, or at the very moment of the Big Bang. This profound disconnect has driven the quest for a theory of everything, a unified framework that reconciles all fundamental forces, including gravity, with quantum mechanics. String theory, born in the 1970s and gaining prominence in the 1980s, offered a revolutionary solution. It proposes that the most fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating, one-dimensional strings. The different vibrational modes of these strings give rise to all the various particles we observe, from electrons and quarks to photons and gravitons, hypothetical particles mediating gravity. The elegance of string theory lies in its potential to naturally incorporate gravity into the quantum realm. However, string theory introduced a peculiar requirement. It only works consistently if the universe possesses extra spatial dimensions beyond the three we perceive: up, down, left, right, forward, backward, and one dimension of time. Depending on the version of string theory, this could be 9, 10, or even 11 dimensions in total. Unveiling the Brane, our universe, as a cosmic membrane. This is where the concept of the brane enters the picture. In string theory, and more generally, M-theory, which unifies different string theories, a brane is a higher dimensional object on which open strings, those with ends, can attach. Crucially, in the Brane multiverse model, our entire universe, every star, every galaxy, every atom, every force we experience, except possibly gravity, is thought to be confined to one such brane. Imagine a single sheet of paper floating in a vast, empty room. To any hypothetical, two-dimensional beings living on that paper, their entire reality would be limited to its surface. They could move forward, backward, left, and right, but the concept of up or down relative to the room would be utterly alien to them. In this analogy, the paper is our three-dimensional universe brane, and the room is the higher dimensional space, often called the bulk, or hyperspace, in which our brane is embedded. The mystery of extra dimensions, large versus compactified. If these extra dimensions exist, why don't we see them? String theory offers two main possibilities: compactified dimensions. Most of the extra dimensions are curled up, or compactified into incredibly tiny, microscopic loops, so small that they are undetectable by our current experiments. Think of a garden hose. From far away, it looks like a one-dimensional line. But up close, you can see its second dimension, its circular cross-section. Similarly, these extra dimensions might be curled up tighter than an atom, accessible only to the fundamental strings themselves. Large extra dimensions. This is where the Brane multiverse really takes shape. Some models propose that at least one or more of these extra dimensions are not curled up, but are actually large, perhaps even infinite, just like our familiar three. The reason we do unperceive them is that the matter and forces, electromagnetism, strong and weak nuclear forces that make up our universe, are fundamentally stuck to our 3D brane. They simply cannot propagate into these large extra dimensions. Gravity's uniqueness leaking into the bulk. This brings us to a crucial and elegant feature of the Brane multiverse model: its potential explanation for the perplexing weakness of gravity. Gravity is by far the weakest of the four fundamental forces. Compare lifting a paperclip with a small magnet, electromagnetism, to the entire Earth's gravity trying to pull it down. The magnet easily wins. Why is gravity so incredibly feeble compared to the other forces? In the Brane multiverse, unlike electromagnetism and the nuclear forces, gravity is theorized to be able to leak out of our brain and into the higher dimensional bulk. Because its influence is spread across these extra dimensions, it appears diluted and consequently much weaker when measured from our 3D brain. It's like a sound wave that gets louder if confined to a small room, but quieter if it escapes into a vast open space. If gravity can traverse the bulk, it would also mean that it could potentially interact with other branes. Colliding worlds and cyclic universes. This idea of gravity traveling through the bulk opens up truly mind-boggling scenarios. If other branes exist in the bulk, separated from ours, their gravitational influence might subtly affect our universe, or vice versa. Some brane cosmology models, like the ekpyrotic and cyclic universe models, propose that our Big Bang wasn't the absolute beginning, but rather the result of a violent collision between two branes in the bulk. Imagine two giant cosmic membranes, floating through a higher dimension, slowly drifting towards each other. When they finally collide, the immense energy released could manifest as the Big Bang, resetting the universe, and initiating a new cycle of expansion, cooling, and structure formation, only for the cycle to repeat again after trillions of years. The Brane multiverse, therefore, paints a picture not just of parallel universes, but of universes that might physically interact. However subtly, through unseen dimensions, it suggests that our entire cosmic existence could be a fleeting moment in a grander, multidimensional drama, where our reality is just one of many cosmic films playing out on a vast, unseen stage. It's a universe of universes, stacked like cosmic pancakes, challenging us to look not just horizontally across the cosmos, but outward into higher dimensions we can barely conceive. From the vast, bubbling expanse of cosmic inflation and the hidden dimensions of membrane universes, we now plunge into perhaps the most bewildering, yet equally compelling vision of a multiverse. One that arises, not from the cosmic scale, but from the perplexing heart of the very small. Quantum mechanics. This is the realm where particles can be in multiple places at once, where observing something changes its reality, and where probability reigns supreme over certainty. It is here that the concept of the quantum multiverse, particularly through the many worlds interpretation, MWI, takes root. The unsettling world of quantum mechanics, superposition, and measurement. For nearly a century, quantum mechanics has been the most successful scientific theory ever devised, accurately predicting the behavior of atoms, molecules, and light. It underpins all of modern technology, from lasers to transistors. Yet, despite its unparalleled predictive power, its implications for the nature of reality are deeply unsettling and defy our everyday experience. The core of this strangeness lies in phenomena like superposition and the measurement problem. Superposition. Before a quantum particle is observed, it doesn't exist in a single, definite state. Instead, it exists in a superposition, a combination of all its possible states simultaneously. Imagine a light switch that is both on and off at the same time until you flick it to check. An electron isn't just spinning up or spinning down. It's spinning both up and down simultaneously. The measurement problem. This is where the true mystery begins. When we measure or observe a quantum particle, its superposition seems to instantly collapse into one definite state. The coin that was both heads and tails suddenly becomes just heads or just tails. But how does this collapse happen? What defines a measurement? Is it the presence of a conscious observer? This collapse is not explicitly described by the equations of quantum mechanics, leading to deep philosophical quandaries. Famous thought experiments like Schrödinger's cat were designed by physicists like Erwin Schrödinger to highlight the absurdity of applying quantum rules to the macroscopic world. If a cat's fate is tied to a quantum event, is the cat both alive and dead until we open the box and observe it? Hugh Everett III and the birth of men. In 1957, a brilliant but then obscure Princeton graduate student named Hugh Everett III proposed a radical solution to the measurement problem that avoided any mysterious collapse. His idea was breathtakingly simple, yet mind-bendingly profound. The wave function never truly collapses. Instead, every time a quantum measurement is made, or every time a quantum possibility is actualized, the universe itself splits or branches into multiple parallel universes, each representing a different possible outcome. For Everett, if you flip that quantum coin, in one universe, the coin lands heads. Simultaneously, at that very quantum moment, the universe branches off, and in a newly created parallel universe, the coin lands tails. And crucial to MWI, you, the observer, also split. One you experiences the heads outcome, and another you in the parallel universe experiences the tails outcome. Both versions of you are equally real, equally conscious, and completely unaware of their counterpart. This isn't about physical travel between universes. It's about the divergence of realities. These new universes are not physically separated by vast cosmic distances or hidden dimensions. They are separated by their differing quantum histories. They are perpetually being created, an infinite tree, constantly sprouting new branches at every single quantum event, no matter how small. The nature of quantum parallel universes. The implications of MWI are truly staggering. Infinite realities. If every quantum possibility leads to a split, then the number of parallel universes becomes unfathomably large, essentially infinite. Every choice you make, every interaction of particles in your brain, every photon hitting your retina, each such event could be seen as spawning new universes. All possibilities exist. This means that every single conceivable outcome of every event, no matter how unlikely, exists in some universe. In one universe, you might have chosen a different career. In another, a different turn of events led to a completely altered historical outcome. In yet another, perhaps the dinosaurs never went extinct. Equally real. Crucially, according to MWI, these branching universes are not mere possibilities or hypothetical constructs. They are all equally real, equally substantial, and equally valid. The you experiencing this reality is no more or less real than the you experiencing a subtly or dramatically different one. No interaction. Just as with the bubble universes, there is no communication or interaction between these quantum branched universes. Once a split occurs, those realities diverge irrevocably. There's no way to cross over or send messages between them. MWI, strengths, challenges, and acceptance. The primary strength of the many worlds interpretation is that it offers a way to interpret quantum mechanics without invoking a mysterious collapse mechanism. The quantum equations are taken at face value. All possibilities continue to exist, they simply evolve into separate realities. It's a deterministic theory in a sense, as every outcome eventually plays out somewhere. However, the sheer extravagance of MWI, the constant, infinite branching of universes, is its biggest conceptual hurdle for many. It raises profound philosophical questions about identity, free will, and the very meaning of reality. If there are infinite versions of you making every possible choice, what does it mean to be you? Despite these challenges, MWI has gained significant traction and a growing number of adherents among physicists and philosophers. Its elegance in resolving quantum paradoxes without additional postulates makes it a powerful contender in the ongoing debate about the true nature of quantum reality. It paints a picture of existence not as a single stream, but as an endlessly branching river, with every conceivable permutation of events playing out in some corner of the vast, quantum-driven multiverse. Having explored the theoretical frameworks that give rise to the multiverse, from the inflationary bubble universes to brain worlds and quantum branching realities, a crucial question remains. Why would serious scientists, grounded in empirical observation and mathematical rigor, dedicate their formidable intellects to such seemingly speculative concepts? The answer lies in some of the most profound, unsettling, and stubbornly persistent mysteries about our own universe, particularly what's known as the fine-tuning problem and the Anthropic principle. The cosmic recipe, a universe perfectly tuned for life. Imagine you're baking a cake. If you alter the amount of flour, sugar, or baking soda by even a small margin, the cake might turn out inedible. Now, imagine the universe as an impossibly complex cosmic cake, where the ingredients are the fundamental constants of physics, immutable numbers that define the very fabric of reality. These include the gravitational constant Gi, dictates the strength of gravity. The electromagnetic coupling constant governs the strength of electromagnetic interactions. The strong nuclear force coupling constant binds protons and neutrons together in atomic nuclei. The weak nuclear force coupling constant responsible for radioactive decay. The masses of fundamental particles, like electrons, protons, and neutrons. The cosmological constant lambda. Lambda represents the energy density of empty space, driving the universe's accelerated expansion. When physicists examine the precise values of these constants, they find something astonishing. They appear to be exquisitely fine-tuned for the existence of complex structures, stars, galaxies, and, ultimately, life as we know it. The range of values that would allow for a life-supporting universe is incredibly narrow. Consider just a few compelling examples of this cosmic precision. If the strong nuclear force were even slightly weaker by as little as 1%, stable atomic nuclei wouldn't form. No carbon, no oxygen, no elements heavier than hydrogen. Without these, complex chemistry and life would be impossible. If it were slightly stronger, hydrogen would fuse too easily, stars would burn out too quickly, and the universe would be filled with heavy elements, leaving no hydrogen for water or organic molecules. If the difference in mass between a proton and a neutron were only slightly different, all protons would decay into neutrons, or vice versa, leaving no stable atoms. The electromagnetic force, if just a little stronger or weaker, would prevent atoms from forming stable bonds or allowing complex molecules to exist. Life fundamentally relies on the precise balance of these forces. Perhaps the most bewildering fine-tuning involves the cosmological constant lambda. Observations show it to be an incredibly tiny, positive number, causing the universe to expand at an accelerating rate. However, theoretical calculations, based on quantum field theory, predict its value to be fantastically larger, by a factor of y-day, a 1 followed by 120 zeros, than what we observe. This discrepancy is so enormous, it's often called the worst prediction in the history of physics. If lambda were even slightly larger, the universe would have expanded so rapidly in its infancy that matter would never have clumped together to form galaxies, stars, or planets. If it were slightly negative, the universe would have collapsed back on itself almost immediately. Our universe exists in a knife-edge balance that seems almost impossibly precise. The Anthropic principle, a question of perspective. Faced with such improbable precision, scientists are left with a profound question. Is this merely a cosmic fluke, an incredibly lucky roll of the dice in a singular universe? Or is there a deeper explanation? This is where the Anthropic principle enters the discussion, offering a framework for interpreting these coincidences. The weak Anthropic principle, WAP, states that the observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist sites where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. In simpler terms, we observe a universe that is hospitable to us, because, if it weren't, we wouldn't be here to observe it. It's a statement of selection bias. We can only exist in a universe capable of supporting life, while the WAP is a tautology, a statement that is true by definition. It doesn't explain why the constants are what they are. It only states that if they were different, we wouldn't be having this conversation. However, when combined with the multiverse hypothesis, it becomes a powerful explanatory tool. The multiverse as a solution to fine-tuning. This is where the multiverse truly shines as a potential answer to the fine-tuning problem. If our universe is not unique, but rather one among an infinite, or at least vast ensemble of universes, each potentially born with different fundamental constants, different numbers of dimensions, or different initial conditions, then the miracle of our finely tuned cosmos suddenly transforms into a statistical inevitability. Imagine an infinite cosmic lottery, where every possible combination of physical laws and constants is realized in a different universe. In such a scenario, it's not surprising, but rather guaranteed, that at least some universes will have the precise conditions necessary for stars to form, heavy elements to be forged, and eventually, for intelligent life to emerge. We simply find ourselves in one of these habitable universes, much like finding yourself on a life-supporting planet in a galaxy teeming with barren worlds. We are here because this particular universe allowed for our existence. The multiverse provides a framework to explain why our universe is so special without invoking divine intervention or an extraordinary stroke of luck. It shifts the question from why this perfect universe to what kind of universe would we necessarily observe, given that we exist to observe anything at all. It's a powerful and elegant solution that resonates with scientific principles, even if the multiverse itself remains beyond direct empirical verification. While some may find the concept of infinite universes an extravagant solution for many physicists, it's less extravagant than presuming our single universe won an almost impossible cosmic lottery. Beyond fine-tuning, the multiverse also offers potential explanations for other cosmological puzzles, such as the surprising uniformity of the cosmic microwave background, CMB, or the seemingly paradoxical flatness of space on large scales, which, as we discussed with inflation, are naturally accounted for in models where our universe is just one of many. While currently without direct observational proof, the multiverse provides a compelling, if unproven, framework for addressing some of the most fundamental questions about the nature and origin of our seemingly unique cosmic home. We've now ventured through some of the most profound and mind-expanding ideas at the forefront of modern cosmology, grappling with concepts that push the very limits of our human imagination, from the ceaseless, chaotic bubble-making of eternal inflation, giving rise to an infinite quilted multiverse, to the subtle hidden dimensions where our universe might merely be a brane floating amidst others, and the startling endlessly branching realities born from every quantum decision within the many worlds. Interpretation: the multiverse hypothesis presents a radical, captivating new perspective on the very nature of existence. Recap of the core ideas and their significance. Each of these theoretical frameworks, though distinct in their mechanics, converges on a single revolutionary idea: that our familiar cosmos, with all its billions of galaxies and its billions of years of history, might be just one tiny singular thread in an unimaginably vast cosmic tapestry. These aren't just fascinating intellectual exercises or fleeting science fiction concepts. For many leading physicists and cosmologists, the multiverse provides compelling potential answers to some of the deepest, most stubborn riddles about our own universe. Chief among these is the astonishing fine-tuning problem, the almost miraculous precision with which the fundamental constants of physics seem to be calibrated, perfectly poised for the emergence of stars, complex chemistry, and ultimately, life. In a single, standalone universe, this appears to be an astronomically improbable stroke of cosmic luck. But within the context of a multiverse, this miracle transforms into a statistical inevitability. If every possible permutation of cosmic laws and initial conditions is realized across an infinite ensemble of universes, then it becomes almost guaranteed that at least some universes will possess the precise environment necessary for complexity and consciousness to arise. We simply find ourselves in one of these habitable universes because, by definition, we could not exist to observe any other. The elusive search for evidence and future prospects. However, it is absolutely critical to underscore that the multiverse remains a hypothesis, direct, empirical, observational evidence. The bedrock of scientific validation is, for now, beyond our current technological and theoretical grasp. The very nature of these proposed other universes often places them inherently beyond our cosmic horizon, making them fundamentally unobservable in the traditional sense. By their very definition, they are typically causally disconnected from our own, meaning light, or any form of information, cannot travel between them and us. Yet the pursuit of indirect evidence continues, driven by the profound implications of this concept. Physicists are constantly exploring subtle signatures within the cosmic microwave background, the relic radiation from the Big Bang, or searching for unique patterns in gravitational waves that might hint at interactions with other branes or the remnants of a prior cosmic collision. Theoretical developments continue to refine these models, making testable predictions, however difficult they may be to confirm. Breakthroughs in quantum gravity or fundamental particle physics could provide unexpected pathways to verification. The enduring wonder and our place in the cosmos, regardless of whether definitive proof emerges in our lifetime. The journey of contemplating the multiverse profoundly changes our perspective on existence. It forces us to confront the limits of our current knowledge, to embrace the vastness of the unknown, and to consider the extraordinary possibility that reality is far grander, more intricate, and more wonderfully diverse than our intuition, confined to a single universe, could ever have imagined. The multiverse is a testament to the insatiable human curiosity that drives us to ask what if, and to push the boundaries of scientific inquiry. It reminds us that our quest to understand the cosmos is an endless one, continually expanding, just like the universe. Or perhaps, the multiverses themselves. In this vast, potential infinity of realities, our existence, while perhaps not unique in the grandest cosmic sense, remains a remarkable and precious phenomenon, nestled within a cosmic unfolding whose true scale we are only just beginning to glimpse. It challenges us to look beyond the familiar, to embrace the unfathomable, and to marvel at the boundless possibilities that might exist beyond our cosmic horizon.